Hi everyone. So this is going to be video 4.5b, which is going to be going back and taking another look at the Routh-Hurwitz criteria and trying to give a little bit more intuition and examples for what we're trying to do. So now the first thing we should do is let's be very explicit about why we care about these roots of the polynomial. So recall, just as a reminder, for difference equations, local stability corresponded to all eigenvalues of the Jacobian matrix had modulus less than 1. So lambda is less than 1 for all eigenvalues, for all lambda I. Okay, and in the last set of videos, we noticed that for differential equations, I'm going to call them ODEs, hopefully that won't be too confusing. So for ODEs, local stability, we haven't explicitly defined this yet, but local stability, by which you mean that all these solutions tend towards 0, sort of corresponds to the idea that all roots of the polynomial, which sometimes I'll slip up and call eigenvalues because they'll turn out to be eigenvalues when we look at the associated matrix, all roots of the polynomial have negative real parts, or are negative real parts, or are negative if they're real. And so now, remember that sometimes we can just directly compute these eigenvalues or these roots, but other times that's a little bit complicated. And so for this, we had something called jury conditions, which were a quicker way of figuring out whether all the eigenvalues have the modulus less than 1. For this, we have the Routh-Hurwitz criteria. Routh-Hurwitz criteria. Basically, we want to be able to say that all the eigenvalues, all the roots of the polynomial have negative real parts or are negative without having to actually explicitly compute them every time. And to do this, we had to go through some amount of formalism. So the first thing we did was to define this really weird matrix called the Hurwitz matrix for each polynomial. And for this, we take each of the coefficients, and here you can imagine we have an A0 here. And you can also imagine you have a n plus 1 lambda to the minus 1, etc. But of course that coefficient is just 0. So this is equal to 0 and this is equal to 1. And so you have things like that, which is all encoded over here in a naught is equal to 1, and then ai is equal to 0 if I is less than 0, so if it's negative, or if it's greater than n, because our polynomial only has coefficients between for lambda to the n through lambda to the 0. Okay, and then we wrote this Hn matrix where for here, as we go along, you subtract the coefficient by 1 as you go along a row. So from column 1 to column 2, you subtract the coefficients by 1. And from row 1 to row 2, as you go down, you add 2 to the coefficients. And so you can do this. And then, of course, a lot of these entries are just 0. So like, for example, this entry over here at the very end, well, that's obviously just 0 so long as n is greater than 2, and so on. So these are equal to 0, or for example, this one's equal to 1, this is equal to 0, this is equal to 0, etc. And over here, this is also generally equal to 0 because you have you only have up through n, you don't have 2n. Okay. And the n-Hurwitz matrices are then, so that's Hn, and then for H1 and H2, those are just the principal minors. So those are, this H1 here is just this here. This H2 is just this here. And H3, oh sorry, you can't quite see that. So H3 here is then this thing. And of course, you can simplify that a little bit by taking h0 equal to 1, sorry, a0 equal to 1, and a minus 1 equal to 0. Okay, so this is a super weird definition, but it turns out to be helpful. And there's a really important theorem in stability theory that says that all the roots of the polynomial have negative real parts if and only if all the determinants of these Hurwitz matrices for hj for j equal 1 through n, if all of them, all these determinants are greater than 0. The proof is way beyond the scope of this course. You can look up the references in the textbook if you want. But we did give the proof for n equal to 2, so the super easy case. So when you're doing that, what you have to do is you have to start out by saying, well, let's write out the polynomial, which is going to be lambda squared plus a1 lambda plus a2. And then this one, it's easy to compute the eigenvalues by just using the quadratic equation. And then the Routh-Hurwitz criteria is that the determinant of each of these matrices is equal to 0. That ends up being equivalent to saying a1, a2 are both a positive. Okay, so then we have a forward case, which is going to be if we start with a1, a2 is greater than 0, and we have a backward case where we start with the real parts of the eigenvalues are both less than 0. So there's a lot of algebra here. I'm not going to go through it all again. You should look in video 4.5a for the details of that. But basically, we were able to prove it for the case of n equal to 2. And the other thing you might have noticed is that there's a simplification of the Routh-Hurwitz criteria, where instead of just starting with these eigenvalues, you can often simplify it to a statement about the coefficients. And so that's what we did in this example here. So here, in this example, we took the determinantial inequalities and rewrote them as inequalities with respect to the coefficients. And as you notice, they get really, really complicated. And so these are a little bit hard to apply at times, but they are still easier than going by the original definitions. Let's go ahead and give an example of this. Let me, just a moment, let me quickly find it. And yeah, so where is my example? Sorry, I'm just taking a look at my notes. Okay, yeah, so, before I give the example, let's go ahead and give a couple more conditions. So obviously using all these conditions is quite complicated. Luckily, if you just say solve part of the conditions, you'll still end up giving necessary conditions, but not sufficient conditions. So, for example, one of the important facts is that you'll notice that here, oh, wait a moment, that should be a 0, not a 2. So hopefully you guys aren't too confused by that. That was a mistake in the last video. But yeah, so in all these cases, you'll notice that the coefficients are positive. And so that turns out actually to be a necessary condition. So if all the roots have negative real parts, then all the coefficients have to be positive. It doesn't go the other way around. So you can have positive coefficients but negative roots. But if all the roots are negative, they have to be positive. We showed that by a direct proof by factoring. And that actually turns out to be a much easier condition to check. So we'll use that in our examples. So let's say this is example 4.6. So let's suppose you start out with d cubed x dt cubed plus a2 dx dt plus a3x is equal to 0. So where a2 and a3 are greater than 0. Well, if you write out the characteristic equation, you get p of lambda is equal to lambda cubed plus a2 lambda plus a3 is equal to 0. So we have a1 is equal to 0, which is not greater than 0. So by corollary 4.1, at least one root does not have positive real part. Positive real part. And example 4.7, which is to say that if you have some more concrete numbers, x triple dot plus 4x double dot plus x dot plus ax is equal to 0. So you have a characteristic polynomial p of lambda is equal to lambda cubed plus 4 lambda squared plus lambda plus a. So by theorem 4.3, need all roots to be negative, have negative real part for solutions to approach 0. And, well, let's try applying the Routh-Hurwitz criteria. So by Routh-Hurwitz criteria, what we need is we need A1 to be greater than 0, A3 to be greater than 0, and A1, A2 to be greater than A3. Now, since A1 is equal to 4, A1 is equal to 4, A2 is equal to 1, and A3 is equal to A, this implies that if A is greater than 0, 4 is greater than, and 4 is greater, this is true if A is greater than 0 and 4 is greater than A, which implies that A is less than 4, greater than 0, for solutions to approach 0. So this is how you can apply the Routh-Hurwitz criteria. It lets you quickly check, especially given some parameter in the coefficients of your ODE, whether or not all the solutions approach 0 as t goes to infinity. Okay, so that's about all for the Routh-Hurwitz criteria. One of the things that's important to note is that this corollary here, this here is necessary but not sufficient. So you can actually come up with examples where for this corollary where you have all positive coefficients, but you don't have negative real parts. So that is an important thing to keep in mind. Let's see. Yeah, let's actually give an yeah, so just keep that in mind. Okay, I think that's about all for the Routh-Hurwitz criteria. We'll be coming back to this a little bit later when we talk about the Kerr-Scoren circle theorem, because we're going to give other criteria for saying that the eigenvalues all have negative real parts. So that's important here, because that allows us to prove that something is stable, because all the solutions approach 0. Okay, thank you very much, and I'll see you in the next video.